Good morning, everyone. Thanks for coming to our talk this morning. My name is Azita. I'm part of the research team here in the Mountain View office at Mozilla. This morning we have Professor Mark Feely and his team here with us from University of Montreal. Our talk, it's in two parts. We have two speakers, Maxime Chevalier-Boisvert, I'm sure I pronounced that incorrectly, is going to be doing the first part of the presentation called Higgs and Monitoring JIT for Java. And then we also have a second part presented by Eric Lavoie in praise of metacircular virtual machine layering. This talk will also be recorded for anyone who wants to listen to it afterward. Thank you.
I can see this one. Hi, so I'm Maxime Chevalier-Boisvert, and I'll be telling you about Higgs, which is the compiler I'm currently working on as part of my PhD research. So Higgs is a tracing JIT for JavaScript. It's written in a mix of D and JavaScript, and it's essentially the second iteration of the Tachyon compiler, which I've presented here and at a conference before. It's an attempt at a more simple and straightforward design and a more dynamic optimization strategy, which I'll be explaining in this presentation. There's three main components to the compiler. There's an interpreter, and there's a tracing JIT, as with most tracing systems. But there's also what I call a type monitoring system, which is used for optimization. The current status is that the interpreter is pretty much complete, and I am actually implementing the type monitoring system, and a tracing JIT will be coming shortly. So previously I worked on Tachyon, which was a method-based JavaScript compiler that compiles JavaScript down to x86 code. And the compiler itself was written in an extended dialect of JavaScript, even components that maybe you wouldn't think as being written in JavaScript. Even the machine code generation, the assembler itself, was in JavaScript. And this compiler was actually self-hosting, which means that Tachyon was able to compile itself. The goal of this project was essentially to combine static type analysis along with dynamic reoptimization, and to end up with something that's a little bit similar to what Brian Hackett implemented at Mozilla with his type inference work. After working on Tachyon, I worked on a type analysis with the goal of maybe making a different accuracy and cost trade-off to come to something that would be maybe usable for a server-side JIT or offline compilation, but that would be maybe slightly more accurate than what would be otherwise possible in a JIT. This analysis was path sensitive and incorporated recency types to try to get more precise inference of object property types. It also used a custom, what I call decouple fixed point algorithm, which I can talk about offline if you're interested. The results that I came to was that the accuracy was actually fairly close to the state of the art in terms of path-sensitive analyses, but there were still some cases where we had difficulty with the precision that were very hard to analyze without context, and unfortunately the cost was still actually fairly high on some programs, even for an offline compiler. And the conclusion I came to was that there's a need for a simpler and more dynamic optimization strategy in this realm. And so this is how I started the Higgs project. So the goal of the Higgs project is to demonstrate the soundness and the effectiveness of a different compiler architecture and dynamic language optimization strategy. The goal isn't to support every JavaScript program out there or to compete directly with commercial compilers like V8 and Firefox on every benchmark, but rather to demonstrate the validity of the strategy itself. And so for now we're making some simplifying assumptions. We're targeting x86-64 only, and we're targeting programs with medium, long running times, so things like games and maybe server-side environments. So why did I choose to implement a tracing JIT for Higgs? Well, you might ask, have tracing JITs gone out of fashion? Because for a while they were very popular in the dynamic language research community. But V8 and Iron Monkey are method-based JITs. And so you might wonder, are method-based JITs simply better? Are they really needed for high performance? I chose a tracing JIT for multiple reasons. One of them is that it allows me to have a simpler design and to build the JIT incrementally on top of the interpreter. There's also some interesting advantages, such that I get basically inlining for free. And there's some architectural advantages, perhaps, which is that I believe invalidating code, invalidating optimizations is very easy to do in a tracing JIT, probably easier than it is to do in a method-based JIT, where you might have to bail out of multiple levels of inlining and things like that. And as a bonus, of course, tracing JITs are known for fast compilation. So the Higgs Interpreter is basically my reference implementation of JavaScript and a fallback for my JIT compiler. I decided to design this for fast prototyping, so the implementation is simple and straightforward, and I prioritized extensibility over having a very fast interpreter design. The interpreter itself is basically a register-based virtual machine with a garbage collector, and it interprets a low-level intermediate representation. The JavaScript primitives, so all the operators are implemented in terms of an extended JavaScript dialect, a little bit like in the Tachyon compiler. And the garbage collector is a very simple semi-space copying collector. So why did I pick a low-level IR as opposed to, say, a high-level intermediate representation? Well, partially because it simplifies the design of the interpreter. So my interpreter only deals with very low-level, very simple operations like integer and floating point multiplication, load, store, call, and return. And it actually knows very little about the semantics of JavaScript on its own. This also simplifies the design of the JIT, because if you're going to implement an intermediate representation that encodes the semantics of JavaScript, you have to implement this in your interpreter, but you also have to implement a JIT that can generate code for all those complex primitives. And I wanted to avoid this duplication of functionality. I also wanted to avoid having operations in my JIT that would require dynamic dispatch inside the operations. So for example, the plus operator in JavaScript takes a very small amount of characters in your source code, but it actually has a lot of implicit branches inside of itself. And you can imagine that if you have a tracing JIT and you want to trace through the execution of the plus operator, you could actually have a method call inside of your plus operator, and this becomes very hairy. So what I did is implement this operator in terms of a JavaScript function, and then the tracing JIT traces through these functions as it would through any other functions. So the JavaScript primitives of my runtime are JavaScript functions. And this is an idea that's maybe a little bit similar to the Tamarind tracing JIT design, which used fort opcodes. So it had very low-level fort opcodes, and then basically it would have the higher-level opcodes implemented in terms of fort functions and things like that. An interesting feature of Higgs is that I chose maybe a different tagging design for dynamic type information than most JIT compiler. It uses what I call double word tagging of values. So it has no tag bits, and it doesn't use a NaN boxing per se. It uses one value word and a separate byte to encode type information. So the obvious downside of this would be it takes more space to encode a value than in another JIT compiler. And if you think, for example, of an array, you're going to be implementing this array as an array of values and an array of types. So an array becomes two arrays, and my interpreter has two stacks. It has a value stack and a type stack that are maintained synchronously. On the upside, it means that my values are accessible directly. There is no boxing and unboxing. I also believe that modern CPUs with their multiple execution units might be able to take advantage of this, because the type operations and the value operations can be executed in parallel a lot of the time. And of course, one of the key aspects of this is that in many cases in an optimizing system, we might be able to completely ignore the type information. In many cases, the JIT knows what the type of value is, and so the type information becomes completely irrelevant. And the hope is that we can avoid touching it completely. So just for illustration, in a tag bit scheme, what's usually done is that the type information is going to be encoded, for example, in the low bits of a word, so the lowest 1 or 2 or 3 bits. With NaN boxing, what you end up doing is that you exploit basically the representation of NaN values, so not a number values in floating point format, to say that your doubles are going to be encoded just as plain old regular doubles, and your other values like pointers and integers are going to be encoded with NaN values. And the way that this is done is that there's a special exponent value that means not a number, and then what you can do is you can use all the lower bits to represent your actual content, your payload of your value. The double word tagging scheme is the one at the bottom. It's the one I'm using in Higgs. Is that I have a full word accessible for my data, and I have a separate byte just to store information. And the reason I picked 1 byte is just because, well, on x86 it's the smallest addressable unit, so it seems convenient. So like I said before, I maintain 2 stacks at the same time. So I have a word stack, a data stack, and a type stack. Another interesting aspect of Higgs is that the runtime library is redefinable. So I can redefine functions of my runtime at execution time. So it allows for things like operator overloading. For example, you could redefine a new plus operator to operate on new custom types that you design. You could reload the runtime library while the compiler is executing. So this allows for a little bit of live coding, if you will. And it's basically just a side effect of my design. I decided to implement runtime functions just like any other regular JavaScript functions. And so just like any other JavaScript function, they can be redefined. I believe that this is a safe bet to make, or a safe feature to keep, because it should be possible to inline the runtime functions like any other JavaScript function, or at least that's the hope. Now I'm going to talk about profiling. So unlike a static compiler, an interpreter virtual machine is able to observe the state of a program as it executes. And this is useful because we can gather useful information for optimization by profiling or monitoring a program as it's executing. And programs tend to have fairly repetitive behavior, so we can exploit this. Unfortunately, there's a cost to profiling, so when the virtual machine is probing at the program, it needs to take some amount of time to do this, and so there's a cost/accuracy trade-off. And what happens is that modern virtual machines in practice do what's called statistical profiling. So they'll profile some of the execution to gather some kind of an approximation, like build an approximate call graph or an approximate profile of the types of values. But the idea is just to use this information to make smarter optimization decisions, generally. It's my opinion that modern virtual machines still don't make fully effective use of the opportunities afforded by profiling. Maybe we never will make fully effective use of all this information, but the fact is that an interpreter can fully observe a program's execution. So any property of an executing program can be observed. And so there's massive amounts of data that are available to us. And it seems to me like we should be able to do more with that information. So as a thought experiment, if you had a program that was executing and you could just freeze it at any point in time, you could actually gather the types of all variables and object fields in your object. If you could scan your heap, you could build a fully accurate profile of all the types in your program at that moment. And it seems like what you should be able to do with something like that is actually pretty tremendous. So the idea of monitoring is basically that it's non-statistical profiling. So what I want to do with Higgs is basically to gather a fully accurate profile of the types inside of a program. So in Higgs, the interpreter is going to monitor the types of all the object fields by recording all types written using special monitoring instructions. So every time that I write to an object property, I want to be able to intercept that and update the type for that property. And then the tracing JIT is going to use this type profile to compile optimized traces that make observations about the types of the program. And of course, these observations might no longer be valid if the type profile changes, and then I'm going to need to invalidate traces to throw them away and maybe recompile new optimized traces. Fortunately, this should actually be very easy to do in a tracing JIT because traces are, by design, constantly, well, bailing out to the interpreter, or they have like a built-in bailout system. So if I can just nullify a trace pointer and exit the current trace if it's invalid, that's basically all I should need to do. So the type system in my compiler should be designed so that most of the optimizations won't be invalidated, of course, because we don't want to have optimizations being made and then invalidated and then being made again and invalidated. I believe we can choose smart heuristics to actually do better at this and avoid repeatedly making the same mistakes, picking smarter optimizations. But I also believe that Brian Hackett showed with his work that some amount of invalidation and recompilation is not the end of the world. You can design your system so that the probability of recompilation will trail off over time. So an overview of the model of what happens inside Higgs or a program would be that the execution of the program is going to begin, and the interpreter is going to start building a type profile through monitoring. And then the interpreter is going to record hot traces as in any other tracing JIT. The traces are going to be passed to an optimizer, an optimizing system, and this system is going to make observations based on the type profile that we have at the moment and simplify and optimize the traces that we've recorded. These traces will then be compiled into machine code, and eventually the interpreter will branch to compiled traces in machine code form. And then the monitoring is going to continue as the program keeps executing and potentially invalidate traces. Of course, this is maybe a little bit of a simplification because those things might all be happening at the same time for different pieces of code, but this is a good overview of the flow of the system. So just as an example, a very simple example here, suppose I have a function init that initializes an array to contain a certain amount of integers, only integer values. And then I have some function that performs a computation on my array. It's going to actually be computing the sum of the values. Now, of course, this maybe isn't so useful in practice, but the idea is that we're going to go through the steps that Higgs would take to optimize this. And optimizing more complex computations like a Fourier transform or anything that operates on an array of numbers would involve similar challenges. So my compute function looks like this in JavaScript. The intermediate representation of the function would look something more like this. Maybe I have some basic blocks with labels. So I enter the function, I initialize my sum and my I to 0. Then I go to my loop test and I'm going to get the array length. So this is going to be a primitive call to the get property method of the array. And then I'm going to compare I against the length of the array. And if I is less than n, I'm going to go to loop body. I'm going to get the current value of the array. I'm going to add that to my sum with the add primitive, which is also a runtime function. And then I'm going to go back to the loop test and keep looping until eventually I reach the end of the array. And then I'll jump to the end and return the sum. So in terms of trace compilers, what typically happens is that we're going to instrument this branch here, and if this backwards branch gets executed often enough, then the trace compiler will conclude that this is a hot trace and it will record a pass through this loop. It will record a sequence of instructions representing this loop. So the trace recording is going to begin here, go through the loop, and then go back to the start of the trace. What's interesting here is that my primitives are implemented in terms of function calls. So basically all of these primitives are going to be inlined in my sequence of instructions for my trace. So my actual trace might look something like this here. So instead of having actual calls to the primitives, I'm going to be inlining the instructions that get executed in these functions. And so what happens basically is that for each of these functions, I'm going to have some guards that leave the trace. So basically these guards are going to be checking that we're maintaining the same conditions that were met during the recording of the trace. And so when I want to get the length of the array, if my input is not an array, then that's not what I saw during the recording of the trace. I'm going to bail out. Otherwise, I'm going to call some lower level instructions to actually read the length of the array in the object. For greater or equal, I'm going to check that both arguments are integer. And if they're both integer, I can use like a low-level machine instruction to do the comparison directly. And so on for all the other primitives. So this is interesting because the trace is already maybe faster than actually like running this through an interpreter. But unfortunately, there's a lot of guards, and these are going to consume a certain amount of CPU time. And for the most part, they might be pretty redundant. So some of these aren't really necessary. So what can we do to optimize this? Well, through monitoring, we can observe that the array R is an array of integers at the entry to the compute function. we actually know its length. If there's only one instance of this array, it's fair to say that we could have observed its exact length. We know that the integers reside in the range from 0 to 999. And from the semantics of JavaScript, we have that I and sum are integer values at their initialization points at the beginning of the function. The result of adding an integer and an integer is also going to be an integer. And array lengths are always unsigned integers that fit within 32 bits. So by propagating the types over the trace and doing a very simple analysis, we can conclude that I and sum will remain unsigned 32-bit integers throughout their lifetime. So quite possibly we can get rid of a lot of these guards. We don't really need to check that A is an array because we know that A is an array when entering the compute function. We don't need to check that I and n are integer here because we know that I is integer when we enter the trace. And we know that array lengths are always integers. So same thing goes for A and I here. And also for sum and for v. We might not be able to eliminate this overflow check with such a simple analysis. We might need a little bit more of a sophisticated analysis. But as you can see, most of these guards can be eliminated very easily. So there's one issue with this, which is of invalidation. So if a trace makes a certain amount of observations about the types of a program, and I optimize the trace based on these observations, there's a danger that the types in the program could change. So for example, what if someone stored a string inside my array of integers? It's no longer an array of integers. Now it contains both strings and integers. So if this happens, if I have a trace that assumes that my array only contains integers, I need to invalidate it and throw it away. And presumably, I only need to re-optimize this trace if it gets executed or if it becomes hot again. If the trace becomes invalidated and is never executed again, I don't need to re-optimize it. Well, there's perhaps another issue, which is that I said that I want to maintain a fully accurate profile of the types in the program. And so I must account for all property rights in the program. I must instrument them all. I must see them all. Because invalid optimizations will cause bugs. I can't allow for invalid optimizations to keep existing in my system once they've been invalidated. But recording all the rights to every property of every object would actually be very slow. So I have to save time, but I have to still account for everything somehow. And as a second example, imagine that you have a simple game where you have a point with x, y coordinates and a velocity vector. And here I have some loop where I'm going to be updating the position of my points. So I say p.x equals p.x plus the velocity times delta time. So this loop could be executed a lot in my program, and I'm reading and I'm writing to p.x and p.y every time, but I don't want to have to instrument both of these writes to p.x because that would take too much time. So what can I possibly do? Well, in this case, it's actually a pretty trivial example because x and y are both floating point numbers, and I know that my delta time will also be a floating point number, presumably. So I have that x is a floating point number plus a floating point number times a floating point number. So I could say, with a very simple, straightforward analysis, that necessarily what I'm going to be writing back here is going to be a floating point number. And so if I start with the assumption here that x is a float, and I see here through a very straightforward analysis along my trace that I'm going to be writing back a float, I don't necessarily need to go and instrument it because I know that that write is going to be safe from the assumptions that I made originally. So I can be a little bit clever when I record my property right. Once I make an observation about a type, I only care to know that this observation remains valid. And I only need to monitor writes that might actually violate past observations. So the observations that I make provide information that we can use to optimize away and remove some monitoring code to make it more efficient. So essentially, it's sort of like we're building a little walled garden, and the types of observations are used to justify the validity of other observations. And what I want to end up with eventually is a minimal set of checks that are needed to guarantee the safety of my program, a set that is hopefully as small as possible. So one question you might ask is, how is this different from, for example, the work that's been done on type inference at Mozilla? Well, one difference, the major difference, is that Higgs doesn't do global type analysis of the program. There is no global fixed point, no complex type inference algorithm. It only does linear type propagation along traces. So this is just like doing just like doing constant propagation along the traces, but where the constant represents types. So it's a very simple algorithm. And I'm hoping that this will allow us to have access to potentially more accurate information than global analysis can provide. Because in my experience, type analyses are forced to be conservative in order to remain valid. And so you have imprecisions that slip into your analysis model that are sometimes very difficult to eliminate. And you might end up with typesets that are actually overgeneralized. But perhaps if you can actually observe the types that actually occur in the program, this will be less of a problem because you'll actually be measuring what is really happening. An interesting possibility for future work with this is the idea of continuous optimizations. So programs may perform different tasks at different times, and long-running programs might be worth re-optimizing later on. So if you think, like, for example, you have someone who's working in some image editor program, and the guy operates on different image formats, then maybe you want to re-optimize your kernels, your operations on the image, depending on the image format that you're working with. And so you would like to maybe forget some previous type information, maybe rebuild your type profile, either partially or entirely. And there could be a variety of ways of doing this. So in conclusion, Higgs will use monitoring to extract accurate type information from program with the goal of optimizing programs, hopefully to a greater extent than otherwise achievable. I am betting on the fact that the cost of accurate type profiling can be offset and optimized away by my JIT compiler. And also Higgs makes some interesting technical choices along the way to further explore the space of JIT design. I will be visiting the Mozilla Mountain View offices until February 15th, and I'm actually here to learn as much as possible about your JIT technology. I'm actually very interested in getting to know more about the optimizations that are done both high and low level in IonMonkey, for example. I'm also very interested in the specifics of your tracing JITs, and so how to do tracing JITs well. And so I'd be very interested to talk to people who have worked on those tracing JITs. I'm also interested in learning in catching details that I might be overlooking in my design. So if you'd like to discuss compilers, programming languages, or even maybe microcontrollers, then please come talk to me. And this is it. If you're interested in seeing the source code for Higgs, it's already available on GitHub, and there's a variety of ways in which you can contact me. Thank you. Quite sure at this point. Actually, this is one of the questions that I'd like to discuss with people who have more expertise of tracing. I've already heard of trace trees and trace linking, but I'm not sure exactly what's the best strategies. I'm hoping to maybe be able to grow trees of code that hopefully cover the entirety of the hot code within a program, so that I hopefully reach a point where I fall back to the interpreter only extremely rarely. But I'd really like to get to talk to people about that. Yes?
I'm sorry.
There's a mic here, please.
Oh,
There's a mic.
I think everyone could. Okay. Oh,
No, it's
for Mozilla. Yeah. Okay. Oh, this is silly. Okay. Okay. Yeah. Now I'm self-conscious. Your type tags. Do they include any notion of object shapes? So for instance, in your example, I think you have a p.x and p.x plus p.y, blah, blah, blah. So one of the things that you need to know there is, oh, well, p definitely still has an x field, right? So do your type tags include some information about object shapes? Forgive me if this is an obvious question. I don't really know much about tracing at all.
The type tags themselves are only 8-bit and are used to represent some very basic information about dynamic types in the program at the moment. So those themselves would only tell you, for example, that P is an object. The type monitoring system, though, would know that P is an object that can have a certain type, can come from a certain point in the program, and it would know information about its fields and also the types for these fields as monitored at execution time. So that information isn't encoded in the type tag per se, but in the types that are being monitored.
And don't you then have to do some kind of interesting alias analysis to make sure that there's not another reference to P over here, and that when I say Q, delete the X field from Q, that Q is not actually a reference to P? Anyway, okay, thank you.
Okay.
So I have two questions.
Okay.
The first one, I guess, which is more specific to Higgs, is how would you compare what you've done to the work that the PyPy people are doing? Is there interesting comparisons to be drawn there?
Yes, I think there are, because just like in PyPy, maybe I'm implementing a part of my runtime is actually implemented in JavaScript, and the interpreter only traces low-level operations. So it is a bit similar in that I'm sort of tracing it at the low level, an implementation of a higher level language, and you could see I could have multiple runtime libraries and implement different languages. I'm not trying to be as general in that they have a framework really to implement your own dynamic language and provide all the machinery for that. But there is definitely some similarity to be drawn.
Okay. The other question, which quite possibly we should talk more about later offline, but just to throw it out there, related to, I think what you said was your earlier work about type propagation. One of the things that we've encountered recently, Shu and I, and some of the work we've been doing, is limitations on the context. Like basically, as an example, when you call like array.map, for example, you would probably like to infer the type of the resulting array separately based on where the array.map was called, as opposed to if the array is created inside array.map, you don't want to conflate all those types together. You lose resolution very fast. Do you kind of know of any good ways to solve this problem in a general way, besides sort of hard coding, this is a function that we know of that should...
Well, I had one idea for trying to solve that problem, which was to not have a context necessarily that's based on who's the caller and who's the caller of the caller, but rather have a context that's based on types. So you could maybe contextualize your analysis of the map function depending on what is the this that the map is called on. So for different array types, you would have a different map function instance, basically. So that would be sort of the idea, and you would hopefully not have too many different map versions. For example, you could have one for arrays of integers, one for arrays of strings, and things like that.
Yeah, it seems like that would also be very vulnerable to conflating types. Like if I have arrays of integers all throughout my program and I'm mapping them to all different kinds of target types, they would all be conflated together, right?
Possible.
So you probably want to contextualize on the function that's passed in too. But, okay, yeah. Thank you.
So your compiler also is written in JavaScript.
Wait.
Sorry. So your compiler is also written in JavaScript. How do you prevent it from tracing itself and then
well,
end up in an infinite recursion?
Tachyon originally was written almost entirely in JavaScript. Higgs, I've actually written the core, the interpreter itself, and the tracing JIT is going to be written in D, so in a separate language. And the runtime library is actually written in JavaScript. So I shouldn't have that problem.
So for the types of programs you want to support, you said long-running programs, since tracing has been shown in the past to not perform very well on short-running programs because they don't reach type stability very fast, and you end up having to drop off trace or retrace over and over because your types are invalidated. Do you have collected like a corpus of JavaScript programs where you think tracing could really be beneficial for it? Because most JavaScript programs are not long-lived.
Well, I think this is a difficult question. I mean, gathering benchmarks for compilers is always a difficult problem in general, because everybody would like to have benchmarks that are very representative, but at the same time, there's a question of what is a representative JavaScript program, what can we do? My approach to this is to say there are some long-running JavaScript programs, like maybe games or maybe Node.js, for example, is the kind of things that I'm hoping to optimize. But I'm also thinking I want to build something that can result in greater performance with some conditions, of course. Like I maybe can't do very well on a program that only runs for 20 milliseconds. But hopefully I'm hoping to open up some possibilities. You know, I'm thinking as JavaScript optimizers progress and we can get better and better performance, that will create new possibilities for applications at the same time.
It'd also be interesting to think about, well, first of all, have you run into any type stability problems with dropping off trace and then having to invalidate much more than you would like?
Well, not at this point, because honestly, I'm maybe a little bit too early in my implementation really to be dealing with that.
Okay, this is a question from Mozilla. So the question is, the mechanism for avoiding monitoring overhead by reasoning about already monitored types seems like it would be limited in scope because it would only be able to reason about other types if they are visibly, if they're visible statically.
Well, I'm actually not sure how to interpret that question.
Yeah, I'm not sure either. I'm just reading.
There are some limitations, I would say. One possibility that I can see is maybe integer overflow and integers versus floating point. Like we would like to be able to say, for example, that a variable is going to be only integer. And we, if we initialize a variable to 0, for example, we will assume originally that it's integer, but maybe at some later point we'll add 0.2 to it. And then we would like to say that it's floating points. So what can we do about something like that? You know, when we're writing back to the property, we would like to check that it's only an integer, and we're going to find that it's not. And so that's going to probably invalidate our optimizations. And we might run often into cases where perhaps, you know, we promote a variable to say it's either integer or floating point. So what do you do about that? Do you want to constantly be checking? I believe we can remove some of the overhead also by widening our typesets. So if we're always running into a problem where we're having to monitor our writes because we say, I'm not sure if it's A or B, then maybe I can just include both A and B in my typeset and sort of give up on that optimization, or just like make the assumptions about those types more pessimistic, and so remove some of the dynamic monitoring overhead that way also.
So someone had mentioned PyPy earlier. So PyPy uses a very limited subset of Python, I guess, in its implementation. I believe you said you mentioned you had extended JavaScript in your implementation, correct? What are some of the things you had to add to the language and why?
Well, basically, I'm trying to implement all of my primitives in terms of JavaScript as much as possible. Well, I'm implementing my primitives in terms of a lower level dialect that my interpreter is able to run and that my JIT is able to compile. So this lower level dialect is going to have things like integer add. So the integer add instruction is going to only manage integers, like assume that both values are definitely integers and produce an integer result for that. So I'm going to have integer add, floating point add, and multiply and bitwise shifts, and then I'm going to be writing a function that will dispatch based on the type of a dynamically typed value to either the integer add or floating point add or
so you're assuming that the operations are not going to take advantage of the loosely typed system, right? It's not going to do any conversion at all between them. Like you said, the integer add is assuming that both arguments are going to be integers.
Well, you have to check beforehand. Basically, the add runtime primitive would check that both values are add before dispatching to the machine.
Right, that's what all the guards are for.
Yeah, and then the tracing JIT would record those dynamic checks as part of the trace.
Cool.
More questions?
Thank you.